Hi, folks. It's great to have everyone online for the first PPS webinar in our interactive series that's going to be running over the next few weeks and months. I'm Charles McLeod, and I lead a lot of the technical consulting activities within the company. And I've got my colleagues, Dr. J, who founded the company over 30 years ago now, and Jackie Ormshire, our marketing coordinator. So I'm just going to give an extra few minutes and I'll bring up the presentation and we'll start with a webinar. Today we're going to be talking about the TactileGlove, one of our most innovative products that can be used in a wide range of applications. I'll talk about how we can use it, how you can deploy it, and what meaningful and valuable data you can get from that. We'll then have a bit of a question and answer session where people can put questions into the chat throughout the talk. And then I will do my very best to work through those questions and not avoid any tricky ones after I have the talk. And then we'll hand over to Denny Yu from Purdue, who's then going to talk a little bit about what he's been doing with our TactileGlove and the exciting and interesting and very relevant results he's picked up. So without further ado, I'm going to kick off here. So hopefully everyone can see the blue screen with a finger on it. That's very similar to my background, but introduces our talk. So I was out at the Applied Ergonomics Society conference last week in Arlington in Texas, and it was great to speak to a number of people around this topic of hand ergonomics. So what we're going to introduce today is how we can improve the accuracy of hand activity level and threshold limit value using the TactileGlove. And this is a real team effort and collaborative effort. This is, while I'm here speaking, I've done very little of the hard work behind the scenes. My colleagues have done great work, and there's a big team behind them too. So who are PPS? Well, hopefully people know us as we've reached out to you, or you've reached out to us in the past, and you're on this webinar for this information session. PPS was started over 30 years ago by Dr. J here, who's on the call, and is always strived to be the world leader in innovative tactile pressure sensors. So hopefully people understand what that is, but if they don't worry, I'm going to explain that in a few slides' time. And while we're an American company, we're very international, we're very worldwide. We've got offices. I'm based in the UK in Scotland. We've got offices across Asia and a number of key distributors, Korea and Vietnam. So we cover the whole international footprint, and we aim to be the go-to provider and effectively target engagement company for a number of innovative, high sensitivity, high repeatability pressure mapping applications. So when did we start? Well, 30 years nearly to the date. We moved out from the Harvard University, where Jay was developing a number of patented innovative technologies in robotic tactile sensing. And what that was trying to look at was how to improve the sensitivity and repeatability of thin film pressure sensors. And the company worked with DARPA on its first few grants to look at how do surgeons use their tools to better perform their operations and their applications. And that was that transition from robotics research into human body comfort and fit, and particularly ergonomics. And that transition has grown over the 30 years of the company, and hopefully you'll see that today as we move on. So what do we do? Well, typically people come to us when they want to measure pressure or force, but we want to look at tactile data, so that distribution of pressure over an area. So looking at the distribution and the quantification of that to understand not just a single value or a single scalar, but actually much more meaningful data around contact mechanics and distribution of loads. Well, what's our technology? Well, fundamentally, all the patents and the reason for our sensitivity and repeatability is based around capacitive sensing. So two metal plates separated by an insulating material. And that insulating material, if you can imagine it like a spring, as we compress the two plates down, we measure that change in capacitance in a similar fashion to how mobile phone screens work, or touch screens that people may have used. But we use that to infer pressure. So by effectively looking at that change in capacitance And having a very methodical calibration process, we're then able to make very sensitive, high repeatability pressure measurements. And we change that stiffness of that spring depending on the application. So whether we might have one sensor that and another one that looks the same to the human eye, is the same thickness, they can have different stiffnesses and in turn give you different sensitivities. So as we've evolved over the years, we've developed a suite of products for hand ergonomics applications. Now, a lot of that was focused initially looking at product design applications, and I'll kind of show a number of those, but also as we moved forward into looking at how users use devices safely and how you can control processes, whether it's in manufacturing or in consumer devices. Our two main product lines now are our finger TPS sensors, which are single element sensors that go across the key regions of the hand. Typically, we have up to 6, so thumb, 4 fingers, and a palm sensor, user calibrated and can give you a force output. What we're going to talk about today is our tactile glove, which we keep innovating on and has 65 elements per hand and is a wireless solution to give us that data, that pressure data, that tactile data across the hand, fully instrumented in real time. So as a couple of examples of what we've been using this for and ones that we can share, instrument design, whether that's in heavy industries or construction, trying to understand how users effectively interact with products and processes. And what we start to see here is this rich data stream that we get from the tactile glove, looking at how people perform different processes, whether it's medical or consumer type applications or recreational, in this case, as the massage, looking at both that spatial distribution and that temporal data that you get from the measurement sensors. In terms of pro sports and athletic sports, that's an area where we see significant traction, trying to optimize performance and effectively ensuring that every athlete, every sports star, or every sport is really maximizing that final inch of performance out of their products or the athlete themselves. And then down to effectively, understanding how humans interact with objects. Again, trying to understand that distribution over an area. But what are we really going to talk about today? What we've been working on is how do we gather much more information than just looking at peak force or peak pressure from a particular product or process? What we're wanting to understand is going from the left here of the single magnet tensionometer, where we're effectively just getting a single value, to then getting that full distribution, showing you where the peak points are, showing you the distribution, and giving you that temporal data over time. And we hope and we believe, and hopefully you'll be convinced throughout this talk, that using that data, that effectively distribution in spatial terms, but also that temporal based time, you'll be able to gather much more valuable insight about your products, about your process, and improve from there.
Listening to this PPS thing right.
I'm going to mute that person, sorry. So what is hand activity level? So hand activity level is something that the ACGIH have defined first in 2001 and then updated in 2018. And it really is a quantification of two key parameters. When you're performing a task or a process, you try to estimate the frequency and the duty cycle of hand exertions. And typically that's done visually right now by participant observation by trained or suitably qualified staff, or in post-process by video. And then alongside that, they start to define normalized peak force, which is relative to either the person's maximum worker strength, a subset of the smaller population or demographic they're working in, or a much bigger database. And what we've tried to do then is, can we then actually capture this quantifiably in the digital world, and actually then use this data to inform how we can then determine what is above the threshold limit value. So the threshold limit values and the action levels, these yellow and red zones, have been defined. They were updated, as I mentioned, in 2018, lowered, as we would expect. Nothing in life is getting higher in that regard. And we want to look at how processes and tasks and objects are effectively monitored. So What does the HAL look like? Well, so the hand activity level goes really from a scale of 0 to 10. And you try to then define, well, in that certain task, are you idle, which would be level 0? Are you doing steady motion, level 6? Or are you doing rapid motions over a continuous period of time, which would be marked 10? And then through those, we've got the normalized peak force, which in these examples today, we're typically normalizing to the actual person performing the task. And we then, when they've squeezed a particular sample or lifted a heavy object, and then we define these two metrics and plot them along the graph. So what you can see on the right here is our tactile glove giving you that spatial data live, giving you the temporal based data. But what we've then done is taken that and then converted that to provide us our hand activity level and normalized peak force indicators. And why does that matter? Well, typically when you're doing these assessments, they're done verbally, they're done observationally by humans. So there's subjectivity, there's bias in the process. What we've tried to do is use this digital measurement system to effectively give us the ability to get repeatable data that's free from bias and fully capturing the hand and area of the hand. So by using the tactile glove, we hope and we believe, and as I say, hopefully you believe too after this webinar, that you get a much richer but much more valuable insight into your process and your products using our tools. So in terms of what we've been doing, well, a lot of users typically of our products would look at, as I mentioned, peak force or peak pressure. And what we were trying to do is look at, could you look at that distribution of the force or pressure over the hand, but also the frequency of it and the temporal based aspects to it. So we were defining effort here as the area under the force time curve. So what we're looking at there is a small force for a short duration is probably better than a high force over a long duration. But then the question comes is, have you got a high force over a short duration or a high force or a low force over a long time? What's better? What's worse? So we're trying to look at that area under that curve. So a simple example that hopefully will relate to many is if you were to saw a block of wood at the house, what would you want to do now? Depending if you're a purist and you're a carpenter, you might want to use some of a really nice manual handsaw. Whether if you're a demolition contractor, you might want to just rip through that with your electric reciprocating saw. So different processes, different requirements in terms of what you're trying to do. What we were trying to look at here was, what if we capture data from each of these different tools doing the same task? Could we look at effort and other metrics associated with this? So this is a quick video, and I sped this up because I didn't want to spend the time just demonstrating a video. But what you can see here in our video, this is our standard tactile glove interface. You've got that color map across the hand, giving you the distribution. You've got the peak forces being plotted at the bottom, and you've got our embedded video and statistical analysis on the right. So that's our standard system that we run. Now, if we look and we run those four different types of saws, the reciprocating saw gives us the highest peak pressure, just peaking about 25 psi there on the index finger. 6 times, just greater than 6 times more than the manual saw. But if we plot the effort, which is really interesting, is that the time for the reciprocating saw is a lot smaller. The area under the curve is a lot smaller. So what we see here is that effectively that effort, as we would naturally and all hopefully agree on, you require more effort when you're using a manual saw to saw a block of wood rather than using these power tools. So hence the invention of power tools. And what we've shown here is that although the reciprocating saw had the highest peak pressure, and if that's all you were looking at, you would then say, well, that's the worst product. But actually then, if you bring in that time-based data, the overall effort reduces. And then when we take that data and we plot that into our threshold limit value graph, we're able to see that actually if you were doing this over long durations, that sawing is a heavy, intensive task. Ironically, the oscillating saw actually comes down into the acceptable levels. There's vibrationary aspects that we need to consider there, but effectively between the pressures and the forces and the time, the other saws actually are above the threshold limit value set in the 2018 data. If we were then to start looking at how people use pens, this was another example that we used. And one of the interesting things here is obviously as we move into computers, people use a lot less pens and papers and things. But if you look there, there's a lid coming off a pen. I always think it's really important to see that kind of quick transition of the pen. But we've gone from a ballpoint pen, a pencil, and then we're going to go into a Sharpie here. And you can see the trend of the actual pressures coming down. There's another lid coming off. But with the Sharpie, the pressures have kind of diminished actually down to minimum. When we plot that effort, what we can see again is that the Sharpie requires the least amount of effort to write along the page. And if we plot that into our TLV value, the pencil, if you were doing this for 4 hours with a force being used on that particular application, could be at an elevated risk level, which is actually quite interesting. If you were really going for it and scribing very, very with a high force, you would start to be at that elevated risk level. Let me just do a mute there. My final application area is if we were starting to look at spreading of glues or different types of adhesives used in many applications from automotive to aerospace. And if we were to take a sort of a spreader design, and then we made which is typically the size of a credit card, and then we were meant to make it bigger, so it was larger, and then we made a much larger one and we put foam around it. We've increased the contact area as we've gone through those design iterations. Well, what do we expect to see? So I think if anyone's done this, they'll hopefully say that design 2 is comfier or less pressure, but what does it actually mean? So, well, if we look at this in real time again, what we can see is when you're using that original sort of thin credit card shaped handle, our peak pressures are actually up near sort of 30 psi. When we move to the sort of the larger handle, the pressures start to come down. So we've got more contact area. We're spreading that out. And then when we go into the foam device, which is just coming up, and I've obviously talked a little bit faster than I did at the conference because I had this timed quite well. But here we go. Here's the foam device. What we can see here is that actually the pressures come right down. But if we plot the effort here, what's really interesting is that when we look at the same amount of glue and we compare the three handles across a very controlled process, the thin plastic one actually is quickest to dissipate the glue. And the analogy I would use here is it's a very similar to a cyclist on the road. They don't have suspension on their bike. When they're racing these bikes along the road, they've got quite a rigid fixed frame to effectively avoid energy wastage. So what again we've looked at there is not just looking at peak pressures, but looking at the time taken to do things across the task. So then when we plot those, what's quite interesting is we get quite a curve, quite a linear curve actually with the different handles. So the foam handle actually does reduce the normalized peak force, but effectively the hand activity level was higher. So we effectively are able to see then, as you shifted the handle design, you can actually work the curve, obviously trying to bring it down as you would want if you were trying to minimize one of those metrics. Clearly, there's a desire to always get down into that acceptable region. These are all based if we were doing this on a sort of a 4-hour window. So what have we tried to show here today? Well, we've tried to show that you can use our tactile glove to gain valuable insights into products, processes for a variety of different applications, whether that's in things like manufacturing and assembly. So I've given some examples here of how you would look at optimizing tool design or process applications. Now we're seeing a growing and very relevant area of trying to capture, measure, and lower occupational health and safety incidents and metrics. So trying to flag either, not dangerous, but necessarily unwanted processes or procedures that have been there for legacy reasons. Clearly, there's a big operation looking at optimizing design of different activities, whether it's handles, grasping mechanisms. And then we see a real kind of strand at the bottom in the medical sphere, trying to understand from a rehabilitation perspective or trying to improve patient recovery or actually making sure that that doesn't happen in the first place by continual monitoring over tasks. We're not quite there yet, but it's something we're always very interested in getting to going forward. But what is coming forward? Well, this will hopefully be of interest to people. We've got our standard tactile glove, and we've been working on integrating that with an IMU, inertial measurement unit-based pose measurement system. And what that allows us to do is effectively start to look at the grasp forces, the grasp pressures, that distribution over area with the hand and finger poses in real time in one unit. So we've been working on that. We've got a particular number of interesting applications ahead of us on that. But hopefully, and I'm going to stop talking right now, is that this webinar is giving you a glimpse into what we do. I think it is a thin sliver and glimpse into what we do, but it's given you enough food for thought to think, can I use the tactile glove to help me gain valuable insights from our products and processes? And I look forward to seeing if there's any questions in the chat. So I've got no questions right now, which is I've either done a terrible job of introducing the tactile glove, or somehow I've slam dunked it and everyone's got all their questions answered. So in the interest of making sure that our question has our thing works, I would ask someone to ask one question so that we can make sure that our question and answer session does, our question input tool in Zoom works. So if someone from the audience could ask even the most basic question, that would be great. But if no one's willing to do that, I don't think I can see anyone. Okay, nice demo. Can you comment on the accuracy of the force measure? Well, so thank you for that question. So that's a really good question. What I would say there is you've got a number of metrics to consider. So our tactile glove is calibrated in pressure, and we want to infer force using the known area of our elements. And the elements in the tactile glove range in size. So they go from 5 by 6 millimeters and up at the fingertip. So a number of them up at the fingertip, going to slightly larger ones as you go down into the palm. And that's a balance between element size and area. So we convert our pressure into force using that area calculation. And clearly, if you have a load that's over that area, we will infer that normal force. We're not looking at vector components of force or anything. We're only looking at perpendicular loading. We will infer that to roughly 2% accuracy. But if you're coming in at angles and your point loading is much smaller than the element size, so effectively if you had a pen with a 1 by 1 millimeter load going over your 5 by 6 millimeter element, we don't know that. We can't infer that. So you would get an error there, and that depends on the contact area ratio and also the vector angle component, and it's much harder to put a number on that one. So I'm happy to take that one offline and kind of go through some examples of how we would do that depending on your application. So be glad to reach out and go over that in more detail. And also thank you for putting a question in the chat and making sure that the system works. If there's okay, we've got another question. How do you calculate effort, or is that the area under the pressure versus time curve, or summation of each force versus time curve? So it's a good question. So what we effectively do is we are calculating the area under the summation of the force or time curves. So we've got the individual force curves, we've summed them up. Now, what I would say is this is not us proposing the be all and end all. This is us trying to show the community, which we're all part of, that there is much more to life than just looking at peak force and pressure. So I really welcome input. One of the things we have proposed was summing each of those force curves and then looking at the area under that total curve. So hopefully we've answered that. And if there's no other questions coming in, I'm going to hand over to a long-time collaborator with PPS, Denny Yu from Purdue, and he's going to share a little bit about what he's been doing with the glove.
Excellent. So I prepared a couple of slides, and just give me a second to see if I could get those going. Okay. How does it look? Great.
Looks good to me. Yep.
Great. Well, thanks, Charles, for a wonderful introduction and demonstration of the technology. For kind of my short presentation today, it's more on the academic side on some of the research studies that we've been running, specifically focused on techniques for estimating worker force exertion. This is a topic that our lab has been quite interested in on it, and we have looked at this problem from multiple approaches. And one of those approaches is focused on seeing or kind of using the tactile glove that Charles and PPS has been describing so far. So the purpose of this is not to go too deep into the technical details, but just to give you some highlights on some of the approaches and methods and results that our work has been looking at or has been finding, and then of course opening up for more information, more questions, and for the audience after the presentation. Okay. Before I start, just a couple quick disclosures. The findings of the papers and results on this presentation has been partially supported in part by NIOSH, the National Institute for Occupational Safety and Health, and also NIOSH ERCs from the University of Michigan and also the University of Cincinnati. Also, part of the support of this work is PPS. Thank you so much for the equipment and technical support as we conduct our experiments. Before I go into the research, just a couple background. I'm currently the associate professor at Purdue University. And for Purdue, those guys that aren't aware, we're right there in the Midwest, Northwest Central Indiana. Fantastic. It's a public university and, strengths in a lot of areas, but we're especially proud of our industrial engineering program, where for this year, US News rated us 1, 2, and 3 in terms of rankings for industrial engineering. Number 1 in online engineering, number 2 in undergraduate education, in fact, 5 consecutive years, and also a bump this year to number 3 in graduate engineering or PhD and master's program. So that's enough of the introduction. Let's hop into the problems that we've been exploring and we'll be presenting in this talk. As a lot of you guys might be aware, and of course, Charles provided us a lot of fantastic examples, is our question is, for the occupational space, is this job dangerous? This is just an image I pulled online of a person lifting. But to answer that question, and this is a task that a lot of safety ergonomists are tasked with to do, as Charles mentioned, potentially manually, do observation. But is there a better way of doing it? To answer whether this question is, this job is dangerous. Well, there's a lot of different approaches to it. And one of the very common one used in the United States is using the NIOSH lifting equation. I skipped a couple steps, but the gist of it is that from this NIOSH lifting equation, let me see if my laser pointer works. It usually does crash, so I apologize. You have an equation here where it takes a couple multipliers, H, V, D, A, F, C. Those are just the characteristics of the job, of the task. How far is the load horizontally from the user, the worker? How high is the load vertically from the worker? How far does the load have to move vertically? And also, is there any twisting involved? And how often they have to do it, and how well is that at the handles? Those are somewhat easily. We have a lot of research and also a lot of technologies, companies, and software available these days that could relatively easily estimate these kind of task factors, location, distance factors. Primarily, I think a hot area to do this is in computer vision. We also have done a lot of computer vision work too, but that's work separate that I'm not going to present in this presentation. So that's step 2, kind of getting these measurements and multipliers hashed out. But to determine whether or not this job is dangerous, you have to calculate the lifting index. And you can kind of see here the RWL, that's calculated from your multipliers from the NIOSH lifting equation. But they need to also, to determine whether this is safe or not, you need the object weight. That is where a lot of our focus is on, as I mentioned in the title slide, is, how exactly can you reliably and easily and at scale measure the object's weight, or how much weight the person is holding. And there's been a lot of techniques in literature, and a lot of techniques that practitioners have been used often, and we're not going to cover all of that. But the one that we will talk about is kind of, how do we use the tactile glove? Sorry, the image is blocking the words. But for hand insertions, force loads, hand loads, they're difficult to measure. What are some ways that we could do it, potentially objectively, and potentially also in real time using wearables? So I'm going to present three very briefly, three little studies that we've done. They're actually pretty long studies, but I'm going to compress it just to highlight the key approaches and the key findings. And these series of studies focused on exploring how you can use the tactile gloves or tactile kind of hand glove information to predict potentially the worker's force exertion. So here is the first study. The first study, this is the tactile glove that we're using. It looks a little bit different. I think this is maybe potentially version 1 of the device. So it's a little bit different than what Charles showed. But the basic concept is the same. There are pressure sensors, pressure sensor array on the equipment, on the glove, and using that pressure, we hoped to determine the worker's force exertion. Our study design, we focused on lifting tasks. This is also expanded to other areas. For the lifting task, we looked in 4 to 6 different tasks. The participants manipulated the lifting load kind of in various different positioning, different starts and stops. And given all the data collected, then we start figuring out whether or not the tactile glove can give us a prediction of the lifting risk. So first, we see if there's a strong correlation between the gripping force and the actual weight. Inside these boxes, we put a huge range of weights. As you can see in this figure here, the weights range from somewhere around 10 to 170 newtons. We also compared it to the mean gripping force calculated with the glove, and the calculation for between pressure to force was already described by Charles, so I'm not going to go into that in depth. The blue line here is the 1-to-1. So we kind of expect that if it was perfect match, the gloves will line up straight up. There's a lot of variation, as you kind of see. This was one of the kind of questions that was somewhat intuitive, that pressure, force, load of the weight would be pretty well correlated. However, when you look at it in a real workplace setting, or at least not workplace setting, but at least kind of looking at more dynamic jobs with a lot of variations, a lot of variables, 6 different tasks, large range of loads, a lot of different participants. I think we had about over 30 participants here. You see some variability, so it's not unexpected. Well, the key thing here is you will notice that there's an underestimation. Looking at this trend, there's an underestimation as the weight, the actual weight of the box, as it increases, the underestimation of the glove gets a little bit more underestimated. But all is not lost. Again, this is just a simple correlation analysis. If you integrate some additional variables, for example, some of the task variables. In the tasks, I mentioned we had 6 tasks. Those 6 tasks had different heights of lifting, different requirements for asymmetry, rotation. There's sometimes lifting, sometimes lowering. There's different boxes that we looked at. If you take all those into account, then your model becomes prediction with the relationship with the gripping force calculated with the glove, with the actual load, gets much better. In fact, after you even you can further improve the model by incorporating subject effects, so the variation between subjects, and that's when we get a pretty good R-squared score, 0.71. So the key point here is that the basic correlation that we showed, covering range of 6 tasks, a lot of different motions, participants, straight correlation is not as simple, but if you add additional information into your statistical model, you get potentially improve performance of your model and prediction, and the relationship explaining the variation in weight in the glove gets much better. That's a very quick review of the first study. Each of these studies, there's a QR code. That QR code takes you to the full paper. So if you want additional details of the design, the full academic paper can be found with that link. This is the second paper that we published. So that was focused primarily on your traditional statistics, mixed effects model, regression, correlation. A big chunk of our team here at Purdue, and really a lot of the academics in this area, we've been our capabilities and our models have been greatly enhanced by machine learning and AI. So this second paper on IEEE sensors starts trying to tackle that problem using an AI perspective and approach. Here's the quick pipeline. You can see that we have the loads, the person's lifting it, they're wearing the gloves. We get the information from the pressure sensing system. Using that data, and this is kind of continuously measuring, we feed it into a deep neural network model. We tried several models, VGG, vision transformers, ResNet, and then see how the model performs in predicting the load weight of the box. This is quite a long paper. There's a lot of various techniques and algorithms that we use to make this happen. But the key point takeaway of this paper is that the machine learning does predict better than our kind of just traditional statistics, where we have to kind of craft features from the raw data and feed it into the model and also incorporate a lot of task factors. Here, the machine learning model doesn't require any of the task factors input. Really, it just requires some crafting, of course, of the real-time data stream. You get a lot of data from these sensors, and there's various techniques you can do to kind of make it more digestible to the model. Here we show both shallow models and deeper models, and we found that the shallow models, given the limitations of our data set, again, only about 30 participants, predicted pretty well, 0.82 R-square value in terms of the model performance. All right, I got one more study. So, no, I think getting 0.7 R-squares, 0.8 R-squares, that's fantastic from the research end. But, if you're going to use this to make decisions on the workplace and figuring out where the injury risks are focused on, you potentially need a little bit more guidance than just kind of how well the glove and the load weight matches up. Our most recent work, and you can find, again, the full paper here on the QR code, is developing this all-in-one system. Our team has a lot of expertise, as you see, in kind of this wearable sensors, computer vision, and also deep learning. Again, we didn't have enough time during this presentation to go over a lot of the other research. But from these techniques and our findings, we published our most recent work developing all-in-one system. And can we just develop a one system, one tool to determine the lifting risk? So the process here, I'll go with this into a little bit more in depth. We have a lot of videos that we've taken during these participant studies. We have a lot of glove data. We have a lot of boxes, a lot of load weights, a lot of different types of participants, a lot of different actions. And in fact, we even doubled the sample size relatively recently that we haven't published on yet. So please follow our team if you want the latest results coming in about a couple months. But from this data set that we're presenting on today, you see that we use computer vision and also the tactile glove to determine an all-in-one system. Specifically, if you remember from the lessons learned in study 1, the glove by itself had some, there were some variations in predicting the load weight, and we found that task factors, the lifting kind of heights, etc., twisting, they improved the model. Well, computer vision, our team has done a lot, and there's a lot out there already, that computer vision, it does a very good job in determining heights, distance, rotation, or those kind of very obviously visible kind of parameters. And we actually took the computer vision work and inputted those parameters into the model and combined it with the force. Going way back to like slide number 3, if you guys remember, we showed the lifting index. The lifting index were the task parameters, heights, weights, no, heights, distance, verticals, twistings, etc., repetition. And then also the load, the lifting load. From our both studies in number 1 and number 2, we kind of start seeing that, hey, we actually can put all this together by combining computer vision and a glove to do an all-in-one system for predicting the NIOSH lifting equation. Here's some more kind of details of the task. 6 different tasks, 31 participants, 19 were males, 80% were right-handed. What we did here was that task 1, 2, 3, 4, 5, 6, they do that twice at, let's say, a shelf at high height. Do it twice again, shelf at middle height. Do it twice again, the whole set of sequence at low height. Then we go for a lifting risk index of between 1 and 2. We call it medium weight. They do it all again. Then we do it kind of on higher weights, lifting risk over 3. And then they do it all again. So a lot of different lifts and various kind of sequences of lifts. For our study, there's a lot of novelty in the studies to make sure we control for a lot of extraneous factors that may influence our model. But one of the things that we did was we counterbalanced the weight. So we see light, medium, and heavy, but in reality, for different subjects, the order of that was counterbalanced and randomized to kind of potentially help eliminate some of the order effects. In summary, from this data set, we had over 3,000 total lifts. And unfortunately, we had some lifts that we had to take out due to missing or corrupted video. After removing those, we had to remove additional 31 lifts due to missing or corrective glove recordings. One of the things to note that for lifting, there's 2 phases. This was subtle in our lifting equation slide. There's the origin of the lift, and there's also the kind of the landing of the lift. And both lifting conditions, the end and also beginning, origin or destination, as what the equation calls it. Both of those can be calculated with a lifting index because they have different parameters. So technically, we have about over 5,000 lifts inputted into our model. And this is the final results, just the key results here. The key results showed that determining the lifting risk, the CNN performs the best. Again, deep learning. We tried some kind of less data-intensive models, didn't work as well. But CNN worked the best, convolution neural networks. The other key finding here is that, again, I mentioned we have computer vision, collecting data, giving us outputs. We have the glove collecting data, giving us output. And computer vision by itself didn't actually perform very well. Just using pose. So a lot of the software, if you're only using software, computer vision metrics to determine the lifting position, the estimation of the lifting risk may not be very accurate because, again, the critical factor here is that force exertion, the load. So when you include the load and the pose, then it matches up with the calculated NIOSH lift pretty well. F1 score of 0.88. The glove also does pretty well by itself, but of course, the another limitation I want to call out is that the task in the real world, the lifting kind of task parameters can be, highly varied. It could be thousands of different types of risk, different types of factors. Here we only examined 6, so the 6 task conditions, they do constrain the model a little bit, so the glove worked pretty well in that respect. So the purpose of this was really just to give you highlights on some of the work that we're doing, focusing on this challenge of estimating force. Specifically, this of our work, we are highlighting the ones focused on the tactile glove, and kind of show potential some of the findings and results and methodology that we've been focused on in our team. I would love to acknowledge, of course, some of the collaborators and students of this work. Jack Liu from NIOSH. We have our PhD student that's been the lead in many of these studies, Boyang. We also have some PhD candidates, PhD students, also been doing a lot of work in this area, moving the research forward. Eric Chen and also Pei-Ren Liu. And of course, again, reminder of our funding support. Well, thank you, everybody. And thank you, of course, PPS for the opportunity to share some more work. I'm very excited with the technology and, of course, the community and the interest in this area. Thank you.
Thank you, Denny. That was fantastic, and I know I've got a lot of questions. If others don't, but I see we've already got a question in here, and we've got two. So the first one is on your first paper. It is interesting that if people are able to lift objects using relatively low levels of grasp force, but many are using much higher levels of force than what is necessary. Why do you think that is?
That's something that I would say is a very big challenge in ergonomics in general, is this subject variability. Um, you know, these are some of the things that can be due to their various lifting techniques, their assumptions of the task, could be order effect. This is quite a long study. They were doing a lot of lifting tasks. We try to randomize as best as we can, but those are all factors that can explain some of the variations we see. Um, this is also leads to our finding that if you do incorporate and explain away some of those subject effects, the model has much better improvements, are able to kind of isolate the effect or isolate the relationship between the detected force and the actual force of the load, required for the load, a little bit better. Again, this is very dynamic. It's not as very simple as just measuring the weight. When we're looking into the gripping force is very different than just the direct weight. I imagine if you kind of have a pressure sensor and you put the weight on top of it, should have a very strong correlation. But you're looking at dynamic motions and moving things over time, could be long time, should be short time. These are all various things that have to do with the subject and the participants' kind of, approach to the task.
Okay, thanks for that. And then the second question is, how does the NIOSH lifting and grasp force in your studies relate to the hand activity level that we discussed earlier on from ACGIH?
Yeah, so I think a lot of ergonomics tools have very common guiding principles. We already know in ergonomics that posture, positioning, force, repetition, these are very key factors that are associated with injuries, musculoskeletal injuries. So given that a lot of these tools have this kind of component focused on postures, has this component focused on repetition, have this component focused on force. So both the NIOSH lifting equation and the hand activity level ACGL HTLV have somewhat of those factors in play. They do target different kind of body region of interest. The NIOSH ones, some of the variables are different because they focus primarily on lifting in the back injuries. And then the hand activity focus a little bit more on the upper extremity. But in general, the guiding principles, I think, are quite similar.
Excellent. Well, thank you for that. So I don't know if anyone's got any other questions, but if they do, please submit them now. But I would encourage anyone to ask questions now, or if they want to reach out to any of us here today that have spoken, or the wider team, please do. Jackie will be sharing effectively our contact details with you, as again, just to make that easy. Hopefully this has been an informative and useful webinar. We're going to run these regularly. Our next one is on the 22nd of April, and that's going to focus on our robotic application range and our new product RoboTact, and how you can use thin film tactile sensors to get you much more valuable data about these automated robotic processes that we will become commonplace in our lives in the years to come, helping us with tasks and our general livelihood. So effectively, the recording will be shared with everyone. That is going to happen towards the end of this week. And thank you all for coming. And I look forward to seeing you at our next series of webinars. And we hope you found this useful. Thank you.